So we have a formal example here, and it says show that F net is equal to the quantity m1 plus m2 times ACM. Well, that's a very mathematical reading of that statement. The meaning of this really is, though, is basically that is Newton's second law, F equals ma. But we're saying if you apply it to two objects that are maybe not connected. I mean, we saw earlier, like we had that example, I think, with the donkey pulling a cart, right? Where we said you can either consider the cart as a system, donkey as a system, or you could look at donkey and the cart combined. But one thing that made that kind of easier to do was the fact that the donkey and the cart were connected and therefore had to have the same acceleration, right? But what if you have two objects, right? So maybe here's the object m1, here's an object m2 at some other point in space, and maybe they're not accelerating in the same way. Maybe they're both experiencing different forces, right? If you applied F equals ma to that, and we made the claim, or at least we kind of learned from Donkey and Ogre in that older example, that you can define systems that have more than one object in it. But again, what do you do if the objects are not rigidly connected? Like, what acceleration do you use? Do you just pick one or the other, right? The answer is you have to use the acceleration of the center of mass, right? And so we saw in the last example that the formula for the acceleration of the center of mass, kind of a vector-based formula, was to just take the two acceleration vectors and kind of do a weighted average similar to how you did a weighted average of position vectors to get a center of mass point. I do want to say actually that this example is definitely one that's getting into some like deeper ideas. It's a very formal example, and I'm kind of like pushing the envelope a little bit here, but there is a point to this because again, it kind of recognizes like what the utility of center of mass is. And when we start looking at collisions in the next topic, we are going to explore a little bit like, okay, for this collision process, what is the center of mass point doing? And it turns out we're not going to necessarily be looking at acceleration, but we're going to be looking more at velocities. But again, the main point of this, though, is that Newton's second law could be phrased in terms of center of mass acceleration. Actually, at a deep level, it turns out it can be shown that if you state that Newton's second law says that the net force on an object is equal to the total mass times the acceleration of the center of mass of the object, if you make that statement, you don't even need Newton's third law or Newton's first law. Originally, Newton phrased his second law as applying to just a single object. And in classical physics, that kind of made sense. We didn't worry about stuff like electrons yet, in other words, in Newton's days, right? Or all the different periodic table. None of that was there yet. Although Newton did himself believe in atoms, it turns out. But nevertheless, in classical physics, modeling a extended object as a point object makes total sense. But Newton always phrased it in terms of a singular object. But when you extend it to multiple objects in this way that this example is doing, it turns out you can do away with all the rest. You can basically take this as the foundation of all of Newtonian physics if you want to. One of the issues that's going to come up here, though, is that these two objects may have internal forces, right? So, like in that sense, maybe they're attracted to each other, possibly by gravity, right? Oops. Let me redraw that. These should be equal and opposite if they're internal forces, so I'm trying to draw it at least so it's roughly like that, right? So there are, like in that sense, there could be like a force of, I'm going to write this one as 2 on 1, right? And that's the usual convention. This is the force of 1 on 2, or at least that's what that arrow there is. But in addition, there could be other external forces, right? So maybe like this one might have some, this could maybe represent the net effect of all the external forces on object 1, right? This one might have some other set of external forces that could be represented like that. And I'm not sure if this notation is going to match what the slide is going to do because I haven't previewed it yet. We're going to see how close it is. But those kinds of ideas are going to be there in order to get to this result from the more basic, Newton's laws that usually only apply to kind of singular objects rather than multi-object systems. But anyway, let's see what it says here. It says each mass can be treated separately by Newton's second law. And so if you look at this first formula here, which mass are we doing here? It says m1 So I think the system for that one is this mass here in my picture, M1. You can see that I've written here, I guessed correctly about the subscripts here. Maybe it's because the same mind did it, right? But this is those external forces summarized, but there's also going to be this internal force that represents the interaction, possible interaction between the two masses in the system, and similarly for the second one, right? But we can add those two up, and you get this really complicated vector equation here. And I've already said, and I want to stress again, if this math is intimidating you, feel free to stop this video and just not watch it, because it's okay. I think you've probably already gotten most of the takeaway from what I've already said. But I think what it's going to say now, though, or the argument is that the forces that the masses exert on each other cancel by Newton's third law. So that means this mass F21 and F12, those two you can just take out. That leaves these two right here. But those two really are summed together, the sum of all external forces on this defined system. Oh, but check out what happened here, right? Because as I did this, right, I had this statement here, but it looks like I've multiplied and divided somewhat judiciously by the total mass of M1 plus M2, right? In other words, this expression here is still here in the numerator of this fraction, but then I multiply by M1 plus M2, so I had to counterbalance that, or, avoid changing the equation by also dividing by M1 plus M2. But neatly, that is the definition of the acceleration of the center of mass. So recognizing that this here is the net force, right? And recognizing that acceleration of center mass expression, we get the result.